Okay, hello everybody. It's a beautiful day. I'm here to maybe it won't be so beautiful tomorrow when you see this lecture, but today it's a gorgeous day, and I'm here to sort of give you some more thermodynamics and follow up on our entropy adventure here, and talk a little bit about the second law and entropy balance. So we're going to be spending a few days on entropy balance in this class, and hopefully to get you guys really up to speed on what it means and how it all goes together. So to start off, as usual, I'm going to talk about the survey from Monday. This survey here, so the question was, which is an incorrect statement about entropy? All right, so again, there's a range of answers. Which is incorrect? Let's see. Entropy is an extensive thermodynamic property, which is right. It is an extensive thermodynamic property. Specific entropy is an intensive thermodynamic property. It's a property that is dependent on the path of a process. So, as we said clearly in Monday's lecture, entropy is independent of path. And that's the whole reason why it's a thermodynamic property in the first place. It needs to be path independent in order to be a thermodynamic property. You can't be dependent on how you get to a thermodynamic state in order to have a thermodynamic property. So that's the deal. Okay, so the other one was it can be applied to reversible and irreversible processes. It can. Entropy can, right? When we calculate the sigma for a reversible process, I mean, what we were doing before is now been expanded. So essentially, we can use this entropy term to define anything for a reversible and an irreversible process from two states. The last one is the change in entropy for a process can be negative, zero, or positive. Oh, this is one of the most confusing things about thermodynamics, right? Okay, so the entropy can go for a process can go up, down, or be zero. Okay, now entropy for overall system, as we're going to learn, must always increase, but for a process, it has to be it can be anything, right? You can go up or down because this depends on where the heat is going. If you're transferring heat in or transferring heat out during a process, for an overall cycle, the entropy needs to increase. So if you're a cycle and you begin and end at the same thermodynamic state and you do some work or you take heat in or release heat, the entropy has to go up for that cycle. But for just a process within that cycle, the entropy can go up, down, or be zero for if it were a reversible process. Okay, so this is an important thing to know about entropy is that it can take any sign. Entropy can. Now what we said about sigma for a cycle, as you remember, for a cycle, then yes, definitely sigma has to be only positive or zero. In the case of entropy, entropy has to be only positive or zero for the case of a cycle. But in the case of a process, that's not true. So, good. Hopefully, we learned something right there. And if you don't understand that, please go back into the lecture. Please go back into the textbook and read about that and figure that out if you can. Okay? Next thing. So today I'm going to talk about entropy and heat transfer. So by inspection of the entropy balance equation, which we talked about before, this big equation here, this is the monster equation we're using for this chapter. Essentially, this is the only equation for the chapter. Remember when I said that there's only two equations of thermodynamics back when we were together in the classroom? Well, what I meant was that the first one was the energy balance, the first law. So that was the first equation that you needed to know, which we've been working with now for a couple months. This is the second one. This guy is the second equation that we have developed. And this is the second equation you need to know. Okay? Of course, you need to know ideal gas law, and you need to know all these other things, but really this is the other major equation, the second law equation, the entropy balance equation is what you need to know. Okay? So let's here's where we say it can be positive, negative, or zero for a process. Just remember, see that. Okay, and here we are. We did an example problem, and now, so I'll read what this says. It's a pretty wordy slide. It indicates that when a closed system undergoing internally reversible process receives energy by heat transfer, the system experiences an increase in entropy. Conversely, when energy is removed by heat transfer, that means energy leaves the system, the entropy of the system decreases. From these considerations, we can say that energy transfer accompanies heat transfer. The direction of entropy transfer is the same as the direction of the heat transfer by our convention. So in, when we say energy in, that's positive. We have positive entropy. Energy out, we negative, etc. So the change in entropy for the system. Okay, resistance energy, yeah. So we say the positive ds equals the positive heat transfer, meaning heat going into the system during a process. Okay. Note that we're not using the cyclic integral anymore here. We're talking about a process from 1 to 2. Okay. Next thing is entropy and heat transfer. In an internally reversible adiabatic process, entropy remains constant. Such a constant entropy process is called an isentropic process. We talked about this already. Remember? We said that the isentropic process meant that we had both adiabatic and reversible, right? So, yeah. So essentially, that means that we can say that the rearrangement of this equation now on rearrangement, the previous equation gives dq equals t ds, right? So we just move the t, right? Move the t, put it in front of the ds, right? TDS, and then we can make an integral. And so q for internally reversible process is equal to the integral from 2 to 1 of TDS. Okay, so we have an interesting equation now. Remember, we had work equals the integral of PdV, and now we have q equals the integral of TDS. Interesting, right? So we can use that. Okay, from this, it follows that energy transferred by heat to a closed system during an internally reversible process is represented by the area under the TS diagram. Okay, we also remember that when we talked about the different diagrams that we can make the PV diagram and make the TS diagram, and I told you that I like those two diagrams because they're the most sort of meaningful with regards to a process. Here's one reason why, right? So if you think about the PV diagram and you look at the area under the PV diagram curve, that's the work for a process. Likewise, when you look at the area under a TS diagram, that is a indication of the, well, if you integrate that, that is the heat that is accompanying that heat transfer. So it's kind of nice to see both of those things graphically, and like you can in this diagram. For an internally reversible process, you can see on a temperature entropy diagram, a TS diagram. Okay, so that's really what we want to know. I'm going to do a couple examples just to keep us moving along with entropy and what's going on with this with the entropy change. I know you did a little bit of homework with this, and I'm going to keep going. I'm going to talk a bit. I have to think most of my problems are actually about ideal gases today. So that's interesting. So we'll talk about ideal gas today. Of course, all these same rules apply to ideal gases or two-phase. It's just a matter of what constitutive relationships you use in order to solve those things, right? What kind of other relationships do you use? Okay, so let's do this. So, oops, it's the first one. So there's two examples I'm going to do, and then I'm going to talk, and then maybe we'll have time for one more example at the end of class. I'm not sure. Okay, so let's see. Let's go here. Let's see if I can unlock my example here. All right, here we go. First example. So we have an example here where we're doing let's see, 1/10 kilomole of carbon monoxide, which we're assuming to be an ideal gas. Okay, and a piston cylinder assembly undergoes a process from P1 equals 150 kPa, T1 equals 300 to P2 and T2. Okay, so we have pressure and temperature of two states. For the process, we also have the work. Employing the ideal gas model, determine the heat transfer and the change of entropy, kilojoules per K. Okay, let's see. Have we introduced everything we need here? Yeah. So A23 delta S equals, yeah, I think we do have everything we need here. I'm just trying to figure out whether we have the right equation for ideal gas change for the change in ideal gas for a, yeah, let's just do it. Okay, let's just do it. All right, there's a relation in here that I'm looking at the solution that we're going to have to explain. And actually, in the next problem, too, there's a relationship that we're going to have to explain there, too, which is good, actually. When you explain these things in example problems, that helps you out, okay? Okay, so anyway, so let's see. What do we have known here? We have a piston cylinder. Okay, we have a piston cylinder with CO undergoing a process. It looks like it's undergoing a compression process to me, right? So P1 is 150 and P2 equals 500, so that's definitely compression. Okay, so undergoing compression, what we need to find is we need to find Q of the process, and we need to find B, we need to find the change in entropy, delta S, and kilojoules per K, so big S. Okay, so the assumptions that we're going to use. Okay, the assumptions that we're going to use in this problem are that, I guess we're going to, of course, the first thing we're going to say, of course, is that CO is an ideal gas. 2, it's not adiabatic because we have Q, so it's not adiabatic. We're going to model, so we're gonna neglect some delta kinetic energy and delta potential energy. Okay, we're going to make a diagram. Okay, well, it's always good to make the diagram of the piston cylinder. So I'll do it sideways so I can put two diagrams on side by side. Anyway, so we have a piston cylinder here that's receiving heat. So Q, and it's doing work, right? But we know that the work is negative, right? So that means work is going in. It's a compression process, so work is going to be negative. You're putting negative work. So this is the system. Remember, it's not a control volume. You don't have gases coming in and out, but you have CO in here. So I'm going to put CO inside. Okay, we can also draw the system on a TS diagram if we want. So for a TS diagram, essentially we're going to operate under the assumption that we have constant pressure lines. And if you remember, like if I just make a mini version, you have this, right, of the two-phase diagram. And then if you have a constant pressure line, it looks like this. It goes straight across the vapor dome and it goes up like this. Kind of like a straight line almost when it gets, and this is gas up here, right? So I'm just going to make this as sort of like a sidebar. Well, we're talking about a region in this zone, okay? Okay, so what this means is that we have a couple of constant pressure lines. One constant pressure line here, one constant pressure line here, okay? And we're going to go for some high pressure. So this is P equals, what did I say? Look at him. So it's all over the place here. P equals 500 and P1 equals 150. So this is P1 equals 150 kPa and P2 equals 500 kPa. Okay, so then you're somewhere up here at some high temperature, and you're down here at some low temperature, for 1. So you're going from 1 to 2. So this is state 1 and this is state 2. We don't know what the shape is. As I said, process is path independent. So, I mean, it's probably unreasonable to draw a squiggly line, like we can't do that. I think that's wrong. So probably looks more like this, right? Okay, so you're going from here to here along some process. Okay, so this is let me just put this up here. Let's see. So T1 and T2. So T1 is as we said, T1 is 300 and T2 is 370. 300. Okay. So that's our diagrams. Those are our two diagrams. It's always nice to make both of those diagrams. It doesn't say make a TS diagram, but I think it's good enough to do. Okay. So let's see. Now what we got to do is negative 300 kilojoules. So we don't know what Q is. So question mark, and we don't know what these two are, 1 and 2. It's question mark. All right, so we know that the heat definitely is the area under that curve. So if we knew what that curve was, we could figure that out. But let's make a model. Let's make some sort of model for this. So the energy balance, so let's do analysis. So analysis is the following. So we have we're going to use the energy balance. So first law, of course mass is constant because it's a fixed mass system. So let's not worry about that. Let's not get hung up on that. The mass is fixed. It's whatever it is inside there. So we're going to have here Q minus W is equal to U2 minus U1. 2 minus U1. And these are all, I'm writing them in big Now we're going to neglect potential and kinetic energy. I'm not even going to write them in there, but we have all these things, right? And notice we're using internal energy because this is a fixed mass system. So we're not using enthalpy in this case. Just remember that, okay? It's not a constant pressure system. We don't use enthalpy here. We're gonna do it this way. So let's see. We know that for an ideal gas, U is only a function of temperature, and we did not say that we use constant specific heats. So so we'll just say not constant, even though it would be a really reasonable assumption. Not a constant CV, but okay. Anyway, so we can look up in table A23. So it didn't say in the problem that we can use constant specific heat, so we're not going to do that, okay? So table A23, let's do here. Excuse me. So yeah, we're going to use U. This is going to be U2 of at some temperature minus U1. And I think in the table it's given on a molar basis for CO, so we're going to have to go the number of moles. Oh, that's going to get ugly. But it's okay. We'll figure that out. Plus the work, because we want things on total. So Q. So this is a relation for Q. So let's go look at table A23 real quick, and then I'll come back to it. So we have the thermodynamic state, so this should be no problem here to just go to just look at this table here. Let's see. I was looking at something else earlier. So let's go to table here. We'll go to the table in SI units. Properties of A23 is here of selected gases, right? CO is one of the selected gases we have. Okay, here we go. Carbon monoxide. Oh, here it is right here. So we're given a bunch of stuff. We're given the change in enthalpy on a molar. Oh, this is kind of messed up. It's kilojoules per kilomole, okay? And you know that the molecular weight of CO is equal to 20. It's a 28, I think. What happened here? Sorry about that. I don't know why it just disappeared. Molecular weight of CO is, well, it's 12 plus 16, right? So it's 28. I should know that. Okay. And then what we're going to do is we're going to look at these different values. So H, it gives you H. What a pain in the butt here. Let's see. Okay, so it's not giving us U. It's giving us S naught though, which we're going to have to learn how to use. Okay, I'm not going to give you any problems to work with this because it's going to be pretty difficult. So it had 370 and 300. So at T1 equals 300, I'm going to have H. Oh no, that gives U. I'm sorry. It's U as the second column. It's just very difficult for me to read it here. So at 300, it's at 6229. So U1 bar equals, what did I just say? 6229 kilojoules per kilomole. And this S naught is S naught bar, which is in moles, is 197.7 kilojoules per kilomole. Okay. At T2, I'm writing these down, by the way. Just want to show you that I'm writing them down. So I'm just copying these down in my problem. Okay. So we have them. So I don't have to go back to the table and do this again. So 370 is down here. So I'm just going to copy these values. 7689. See, T2 is 370K. And then we have U1 equals 7689 kilojoules per kilomole. And S1 naught, which I'll tell you about. This is a pressure normalized value, meaning that because entropy varies with both pressure and temperature for ideal gases, which we're going to learn much more about in the later part of this chapter, we need to know the entropy normalized value for entropy. So S1 is, or I'm sorry, these are two. S naught 2 bar is 370, which is 203.8. kilojoules per kilomole K. Okay, so then these are our properties, and then we know the molecular weight, so we can get this thing done. So so the number of moles. Wait, this is molecular weight, so kilojoules per kilomole. So this is actually here, because this would have to be per kilomole, and it would be divided by molecular weight, right? Because then that would give us kilograms, right? And then you'd have here the molecular weight, and then you'd have the mass. Right. Okay, do we have the mass? Let's see. I guess we would have to calculate it. We don't know the volume. So let's see what happens here. Okay. Oh, wait. Oh, yeah, 1/10 of a kilomole. There we go. All right. I was missing one piece of information. So we have a kilomole, a 1/10 of a kilomole, which is 0.1 kilomole. So this is here, 0.1 kilomole. Now think about it. 1/10 of a kilomole is the, so if you have a certain amount of moles of a substance in there, you have the same. It's the same. It's like the mass conservation. The number of moles remains constant. So if I just say mass is constant, where did I say that? I just want to write this down somewhere. So mass is constant, as is mass is constant, and n equals constant as well. Oops, sorry. I'm gonna write this down here. N equals constant as well. Okay. So number of moles is n. So m over n. So actually, we don't actually need this. We don't need this guy here. See, I'm learning here as we go along. All right, so number of moles, right? Okay, so then let's just solve this. With the Q, we have everything we need. So Q equals n times, well, we just put the numbers in. Let's put the numbers in. 0.1 times U2 minus U1 bar, which is 7689, minus 6229. And then we also have plus minus 300 kilojoules. And so then we're going to end up, we plug this in, we're going to get equals negative 154 kilojoules. Means that you have heat leaving the system, right? This is heat leaving, or heat loss. Okay? All right, so B is to find the delta S. Delta S, okay? So finding delta S with the data, so we have delta S is equal to, okay, so here's an equation that you don't know yet and that we're gonna learn. So since I said that delta S is both dependent on, so U and H are only dependent on temperature, S or entropy is dependent on pressure and temperature. So we can't just say that, but we can look it up using S bar, or S naught, I'm sorry. So the number of moles times S naught 2 minus, these are little s's by the way, minus S naught 1. All right, but you say that has to be dependent on pressure. There's another relation which we'll develop later, okay? R bar natural log of P 2 over P1. So I'm going to just say for now, okay, don't get bogged down in this. This is a pressure correction for entropy change, okay, between two states. All right, so don't worry about it. These are table values. Okay, table values, and that's the pressure change, okay? So don't get bogged down, but if you need to look up entropy for ideal gas in the table, this is where you get it, right? For water and water vapor, you can actually understand the pressure, the entropy, because you're given both pressure and temperature, right? For instance, if you look it up for steam tables and superheated, or if you look it up, it gives you both pressure and temperature, so you know the pressure temperature dependence. In the case of this, you don't. Okay, so you have to, in the ideal gas, you have to kind of make this pressure correction factor. Anyway, so if you plug in the values, so I don't belabor this, 0.1, and it's times, what did I say, 203.8 minus 197.7 minus R bar is 8.314 times the natural log of the pressure ratio, which is P2 over P1. It's high, right? It's high to low, so it's 500 over 300, or 500 over 150. I'm sorry, 500 over 150, right? Did I have that right on my diagram? Yeah, I did. Okay, and then it goes like this. And you've got 0, what, so you have a negative here, 0.3891 kilojoules per kilomole. Oh, I'm sorry, kilojoules per K, because I already, kilojoules per K. So it's a negative, so entropy is negative. You have a delta S of a negative delta S in this case. So entropy is decreasing, okay? Don't worry about it, because that's totally normal. As we said, entropy can go any direction for a process. If it were a cycle and we had negative entropy, we could be in trouble, but that's the way it is, okay? So anyway, so that's the deal. The next example that I want to do, it wants me to rate notability. I think it's doing pretty well. What do you think? Okay, I'll give it an A star. No, I'm not going to write a review while I'm giving the lecture, okay? But I do like it. It's working really well, and I'm really happy with it. Much better than document camera. Some of you have given me feedback on that. The nice thing is that you don't see my hand, because my hand would obscure the camera. So I think it's going pretty well. So the next example, I'm not going to bring up the slides. For the second example, we're going to do. We're also going to talk about an internally reversible process. Reversible processes. So let's talk about nitrogen undergoing an internally reversible process from 6 bar, during which PV equals 120. The initial volume and the work for the process is given. So do you remember what this is called? Here, I'm going to write. Do you remember what when we have this thing? I'm going to put it in orange. This process. All right. This process means it's polytropic process. Okay. All right. So now I want to go through a little bit of an example of what we do. We understand for a polytropic process. Okay. Because I know I didn't do like a very good job. I feel kind of like I did a poor job with regards to explaining polytropic processes to you when we were in class. I kind of blew right through it, and then people have had a lot of questions and comments about polytropic process since then. So what I'm going to do is I'm going to talk a little bit about it here in a minute. But first, let me set up this problem, and then what I'm going to do is I'm going to go back and make it maybe a separate note, a separate example to talk about polytropic process, okay? But so let's just set the problem up first. Okay, so let's go. The initial volume is given, and you have work. Work for the process is positive, means that you have probably work out of the system, assuming ideal gas behavior, and neglected kinetic and potential energy effects determine heat transfer. Okay, and entropy change. Show the process on a TS diagram. All right, so let's see. So we know that it's a reversible process. We know, so one thing is also good to know is that even though it's a reversible process, it doesn't mean that the change in entropy is 0. It means that the change in entropy is at the lowest it can be, right? So it doesn't generate entropy. It's the lowest entropy generation possible. But there's always entropy generation even for a reversible process, okay? For an overall system, the overall entropy change can be 0, but in this case, we can have entropy generation, which we'll see. Okay, so what I want to do is first I'm going to say known. I'm going to just call it we'll call it a compression. We're going to call it an expansion process of nitrogen in a closed mass system. Yeah, because it's a closed mass system, the initial volume and then change volume. I'm going to assume piston cylinder because that's what I like. You might assume like a balloon or something else. It could be a balloon going bigger and smaller. I don't know. I get it. But piston cylinder is always the easy thing for me to understand. Okay, find. Let's see. What we're supposed to find is we're supposed to find the Q for the process, the entropy change. Oops. entropy change, and we're also supposed to show a TS diagram. All right, we can do this. Okay, so let's first let's look and see what we've got in terms of assumptions we can make our life easier. So assumptions, we're going to say A, the first assumption is we get an ideal gas. B, we're going to make the assumption that we're going to neglect, just like the last problem, delta kinetic energy and delta potential energy. So neglect both of those kinetic and potential energy changes. Anything else that I'm missing here? I don't think so. Oh, well, we're going to say it's an internally reversible process. We're going to call it internally reversible. Polytropic process. Okay. I see. Okay, that's a little equilibrium. Okay, fine. I think we're going to just assume that these things, we're going to make a diagram. Yeah, so we don't know everything about this yet. We know from 6 bar to some other thing, and we know the work. So I'm guessing here that this is, since the work is positive, that this is an expansion process. It's just my guess. But I mean, I'm assuming here that if we have a piston cylinder, I'll just draw that like we did before, and we have a piston cylinder, and this is our thermodynamic system with nitrogen in it. So you have nitrogen, you have a volume 1 equals, what is it? Volume 1 equals 1/10 of a meter cubed. Here's your piston and cylinder. So this is your system. So that's your thermodynamic system. And then I'm gonna start the TS diagram here, okay? Even though we don't know exactly everything that's going on here, but we have to make the TS diagram. So we know that you're going to be going from some, you can call it 6 bar. I think we're up here somewhere, right? So 6 bar, 247. I always do this and put this in the wrong place. Okay, so this is 247 degrees C. That's ugly. Okay, so 247 degrees C. And then that's not that much better. Okay, we know that P2 is going to be something like, let's see, P2, we're going to go, the temperature is going to reduce, and P2 is going to come down here somewhere. So we know that's going to happen. I guess we could always make a TS diagram, a PV diagram, I'm sorry, of this thing. So if we made a PV diagram, let's just make a PV diagram. So a PV diagram looks like the following. We're going to go for some high pressure. So we're going from 6 to 6 bar to some low pressure, which we don't know, some P2. We don't know the volume either, so we don't really know much. We just know the work that we put into this. Now, I think that the lines of constant temperature in our PV diagram look kind of like this. But I mean, I'm not entirely sure. They're pretty close to that. Okay. So, anyways, we know this is at 520 degree. I'm sorry, 520 K. Right? That's what they tell us. And then yeah, 247 C. And then we don't know the second temperature. So T2, P2 are unknown. All right. Wow, there's many things we don't know here. So I guess what we want to do is we want to model. The first thing we have to do is do the work. So for the polytropic process, we know, first of all, we're going to find the work. Well, we know the work, but we're going to find the different, we're going to use the work to find the second volume and the second pressure. So we can actually use the polytropic process equation that we developed back in chapter 3, I think, V2 V1 PdV. Okay, so we know, remember PDV, right? That's something we remember for sure. And then we want to know here, we want to do P2V2 minus P1V1 over 1 minus N. This is for a polytropic process. Let me just do it in orange here. Polytropic process. If we were to take this equation, okay, and we were to put it in terms of temperatures by using PV, so we know PV equals RT, right? Well, we know PV equals MRT if we know big V and little v, right? So so essentially we can convert this thing, since we know that some of the temperatures and pressures, and we can mess around with the things that we do know. MRT2 minus T1 over 1 minus N. And we already know N, right? Because N is 1.2. Because that was given to us in the problem here, 1.2. Okay, so we know this and we know that, right? And we know the work. So we can find, okay, so first thing is we can find the mass, because we're going to need to know the mass in order to solve for the temperature. So first thing is find the mass, because we know state 1 pretty well. So we know M is equal to P1 V1 over R bar over molecular weight. Oops. Over, let's see, molecular weight times T1. And then so we can just put our values in for this. So this is at 6 bar, which is 600 kPa approximately, times 0.1. Keep my units right. 8.314 divided by 28, which is the molecular weight of nitrogen and CO, both the same molecular weight, by the way, but makes it a little confusing. But then this is times 520, which is our first temperature. And so this ends up getting us a mass of 0.3887 kilograms. So that's how much mass we have inside the cylinder. And then T2 we can find pretty easily. How am I doing here time-wise? Okay. We're not going to get to my second example, but that's okay. We have plenty of things we can work on here. So T2, we can solve from our equation here, right? So let's just not make a big mess here. So sorry about that. Let's just go like this. So T2 here. So solve this for T2 because we have everything else. So let's just plug that in. So it's 121.14 kilojoules, which is the work. 1 minus 1.2, so it's 121.14, right? Is that what they said? Why it's so specific to the decimal, I have to the hundredths place, I'm not really sure. I'm always, as I said, always perplexed at why we use such precision in thermodynamics, but 0.3887, which is what we had before. Calculated 1.314 over 28, which is the molecular weight, and then ends up giving us plus 520, which is giving us 310. So that's the second temperature. Still not what we need, right? Because we're trying to find Q. Okay, so but that's good. That's an intermediate thing we need. Now, since the final pressure is known, we can find the final pressure. Now, here's where we can use ideal gas law and the PV n equals a constant to solve for P2. All right, so here's where I screwed up. Okay, we got to the part where I screwed up. Okay, so just as an aside, for a polytropic process, okay, we know, and I should have done this back in chapter 3, but that's all right. Better to do it now than never, right? So PV to the n equals a constant, right? So which means that P1V1 to the n equals P2V2 to the n. I know I didn't do this because I know I didn't want to do any derivations in class, and I just forgot to do a video lecture on this. I'm just remembering that now. But anyways, it's not really a derivation. It's really, it's a very short derivation. But anyways, you get this idea, right? So P1 V1 to the n equals P2 V2 to the n. Now, we just take this and go P1 over P2 equals V2 over V1 to the n. Follow me so far? Okay, we got that. Now what we're going to do is we are going to take the ideal gas law and let's see what I'm going to solve for. I guess I'm going to solve for P. So P equals RT, or as M RT over V, right? So if we just put this in here, you're going to get MRT1 over V1 over MRT2 over V2 equals V2 over V1 to the n. All right? Stay with me here. Stay with me. Okay, we can cross these off because the mass is constant and the R is not changing, of course. So then what you're going to end up getting is T1 over V1 over V2 over T2 equals V2 over V1 to the n. There we go. And so all we have to know now is essentially that in order to solve for this, we can get a function of temperature and volume together, right? So let's see, T1 over T2 is equal to V1 over V2 to the, let's see, V2 over V1 to the n. And then so we can get the following ratio here. Let's see if I've done this right. N minus 1, right? V2 over, yes, okay. So we can actually take the inverse of it all, right? T1 over T2, because we really want to solve for T2 over T1. So T2 over T1 then becomes V1 over V2 to the n minus 1. Okay? Yay. Pretty easy, right? So now you can actually relate a bunch of things, because now we can also say that this is equal to P2 over P1. If we do the same kind of process, the n minus 1 over n, right? Because we could plug back in and get pressure back and for the volumes by using the ideal gas law again, and it all just gets very circular, right? Using similar method, right? And so we get these relations. These are important relations, right? They're important. And we're going to use them more for ideal gases, right? They're really important when you use for ideal gases. This is for ideal gases only. Okay? All right, just remember they're for ideal gases only. All right, so back to our problem. Now we've solved that. So now what we can do is we can find P2, because we know that P2 is equal to P1 to the n over n minus 1. Oops. I'm sorry, temperature ratio. So the temperature ratio T2 over T1 to the n minus to the n over n minus 1. Rearranging this equation. Okay? So then we got that. All we got to do then is put our numbers in. And so P1 is equal to, what did we say? Oh my gosh, I forgot about our problem already. I've been so caught up with this stuff. So the problem was that, let's see, P1, what did we say? 6 bar? Okay, all right. Going back down. This is a long example problem here. So 6 bar, we'll just call it 6 bar. Because it's a ratio, right? So it doesn't matter. 310 over what our temperature was 310 over 500 or 520 at the initial, and so it's 1.2 over 1.2 minus 1, which is 0.2. And so example 2 continued. So P2 is then equal to what am I doing in time? All right, almost done. So P2 is then equal to 0.2693 bar. So we go back up here, you know, where our diagram, and we'll go back to our diagram in a minute. All right, so now we can finally use our energy balance now. So Q then is equal to MU2 minus U1 plus W by the first law. And we know that we can find U1 and U2 on a molar basis from the tables, which I'm going to use the same tables, A23 tables. Right, so we can go equals N U2 minus U1 plus work. So that's cool. And so if we look in the tables, I'm running out of time, so I'm just gonna put them here. So U1 bar is equal to 10.848 kilojoules per kilomole. And U2, as a function of temperature only, as you recall, is 6.437 kilojoules per kilomole. Okay, and then let's see, do I know what the entropies are as well? I know, yeah, I know S1 naught. This is the same thing we were doing before. So S1 naught is 207.8 kilojoules per kilomole K. And S2 naught bar on a molar basis is 192.638. 92.6 kilojoules per kilomole. Okay. So now we have all our properties that we just looked up in the table that you didn't see me look up, but I did just look up because I have the solution. Okay. And so anyways, we get Q. Did I solve for Q yet? No, I didn't solve for Q. So let's just solve for Q finally. This is a long drawn out problem. So we have mass, so we can just go 0.3887 times 6437 minus 10.848 divided by, molecular weight, which is 28, because we have to keep it on a mass basis now, plus 121.14, and this ends up giving us 59.93 kilojoules. Okay, so that's the answer to part A. B, we can find the delta S. So we're just going to say S, remember S2 minus S1, big S2 minus big S1 is equal to mass times S1 S2 minus S1 over molecular weight minus the correction factor P2 over P1. So entropy change for an ideal gas. Okay? All right, so then if we do this, we plug in our values, we end up getting, so I'm just going to plug in, we end up getting delta S is equal to 0.1478 kilojoules per kilogram. So it's positive. We have entropy generation. So if I just go back to our TS diagram that we had drawn way in the first page here, here's our TS diagram, right? Okay, so what we've got then is a temperature entropy diagram that looks like the following. So you have one, remember we were at 570 here. Let's just put that in. It's 570 here, and this is K. And then remember we were down here, we have 310. So we know that. So that's the constant values. And then we have a process that goes from here to here, right? And then we know that S2 and S1 are known. I'm not going to put them in because I know them in a molar basis, but we know delta S, right? S is here. So this is 1 and 2. So there's your TS diagram. You don't, just because I say TS diagram doesn't mean you need to actually put the numbers on. You can, but in this case, not necessary. Oh, and the pressure is 0.2693 bar. Okay. So anyways, that's your entropy change for the day. I think we didn't get very far into this thing, but Yeah, so we did that, and now we have to go and talk about closed system entropy balance for closed systems and entropy production. So we'll talk about that. That's one step further beyond what we've done before, but hopefully give you some homework problems. You can try them. And one last thing, I know we're at the end of the lecture, and maybe you're not even with me anymore, but I'm planning to hold the exam, the midterm exam, on the 16th of April. That is next Thursday, on the same time as the discussion. I will send out an announcement, hopefully tonight, to that effect. The exam, I'm thinking right now, is going to be only 50 minutes long, open book. You will turn in whatever you can within 50 minutes, like a homework assignment, essentially. This, I think, is going to be really tricky for some people, but I don't know how else to do it in a fair way that doesn't give more people more time than others and cuts down on communication. I do not intend to use any proctoring software, Proctorio, or any of those things. I just can't see doing that. And I want to make sure everybody gets a fair try at this. So I'll try to make a reasonable exam for 50 minutes that will be available essentially right at the time of the start of the discussion, and we'll go right to the end, and then you'll have that time to hand in your assignment. I know many of you have classes right after discussion, so I won't be extending any time for anybody for the exam. Unless, of course, you come to me with some disability services letter or something like that, then I can make accommodations for you. Okay, that's it. Thank you, and I will talk to you again on Friday.